today I will talk a little bit about our work that is related to how to use like opcode. With opcode, you can do covenant and you can also do like start proof verification. And like this will be a very long talk, like there are about 50 slides. So if you have any question in the middle, you can stand to the front, and that like we will take questions as in the middle. Okay. So I will start to talk about from like the Bitcoin programmability. Is that like if we think about Bitcoin programmability, we can also think about what EVM is and why EVM have what we say good programmability, but Bitcoin does not. Well, actually, Bitcoin and EVM are kind of quite similar because arguably they are both like state machine. They also are both run by opcodes. In some ways, that Ethereum is actually kind of very similar to Bitcoin, and you can probably need to believe that like Ethereum was inspired by Bitcoin in some way. Well, EVM, however, is a little bit more powerful than like Bitcoin scripting. First of all, EVM smart contract have the state, so they can keep data. This enables a lot of the application like ERC20. You can also do function calls. A contract can call another contract. The next thing is concurrency, is that like you can have many users sending the same transaction then call the same contract, and that can happen in the same block. And that you also have some crypto accelerator, like for example, you have like, EVM have some pre-compiled like opcode. You can basically say them as special opcode that have you to verify zero-knowledge proof. And the last thing that EVM can do is that you can actually just run like, it's almost like an opcode that is used to send like, for example, like ETH to somebody. Bitcoin doesn't have this like functionality, and the reason why have to do with the like Bitcoin script. So Bitcoin is a stack machine. You have a stack, and if you put the opcode, like for example, OB_add, it can two numbers, add them together, and put it back to the stack. While Bitcoin have a lot of the opcode, you have like, Bitcoin already have a lot of the opcode. You have if else. This is actually already quite powerful. You can do some simple mathematics. You can add numbers together. You can subtract them. You also have like some opcode to do hashing. And lastly, I think just say verify probably is the most like frequently used opcode. One of them is that you can also verify the signature. But what is the problem is not about like the opcode that exists, it's about the opcode that doesn't exist. And here I actually firstly want to show you an example about what would be the opcode in practice. Like, well, most of the opcode that we are using today on the Bitcoin blockchain are just simpler one. You only use that to do, for example, pay to like business like public key or something like that. But if you start to use like Bitcoin to do actual programming, you are going to have like script that look like this. I showed this picture to kind of tell you that like we clearly need a better way for user, for developer to handle the script, not something like this. Okay. But Bitcoin doesn't have some of the opcode, and I can just give a few examples. First of all, Bitcoin doesn't have opcode that multiply two numbers together. This is not like horrible because there are ways to not do that. Like there are ways to do the multiplying without using the multiplying opcode, and that like we already know that you can use like opcode to kind of simulate what opmod is doing. Basically, you do a big decomposition. You perform the multiplying like using double and add, and that can give you a multiplying, although it's not as efficient. You also don't have like XOR. You cannot just like do what we call bitwise like exclusive OR over some value. But this is also not a fundamental like limitation. If you can like cut the number into smaller chunk, you can actually use a lookup table to do XOR. So I would say these two are examples where that some opcode are missing, but you have actually ways to like emulate them. You can bypass that limitation. But there are also some opcode that like if you don't have them, you don't have them. First of all, there is no those opcode that I say like OP send BTC, OP get like, for example, transaction input, get output. You don't have them. And you are actually kind of provably cannot bypass that because the only opcode that actually give the script the power to know what is like happening in the transaction is that like check signature verify. Well, there are some opcode doing the log time, but basically that if you really want to see the rest of the transaction, all you have to do, you have to go through like the signature. And that kind of give you an idea that like, okay, with the current opcode, it's probably like that impossible to do have general purpose like covenant because you cannot do like either one of these. By the way, I think here is also one thing that we should try not to if we want some feature from the Bitcoin script, we shouldn't always think about that we should create a name for that, right? You will have a bunch of the OP something later on. Well, but I think the last one is this, is that in Bitcoin, we also don't have opcat. If you have two strings in the stack, one is a bunch of the A, one is a bunch of the V, and that if you don't have a way to kind of combine them together, by using those multiplying opcode, the integer opcode, then there is actually probably no way for you to easily concatenate them together. And why is provable is just that there is just so many opcode. You look at them, it's actually very easy to know that okay, there is actually no way to do that. Okay, the consequence of that is that there are two consequences. Some operations are still possible, like multiplying. They are just going to be much slower. Well, there are also the second consequence is that you have some functionality that are just impossible. And you can almost prove that by just looking at the not so many opcode and quickly get a conclusion is that you have to go through signature verification, but you cannot do something very useful with the signature verification without these opcodes. And I can give you two examples about applications that are kind of enabled or disabled because of this. You can do Merkle trade today, and that you can just implement the hash function entirely in the system. And by the way, this number is not right. I need to change that. I think the best result right now is 75,000 script for hashing 112 bytes. And for using Blake. And this is also the only best hash function that can be actually implemented in the Bitcoin. All you need to do is that you need to simulate all those operations using, actually, eventually, this is a purely lookup table-based implementation. It would be expensive. If you want to do every layer of the Merkle trade, not the entire trade, just a layer, you will need to pay about $15 in transaction fee. If you are trying to use a Merkle trade to build some very fancy memory using Merkle trade, just changing a leaf of that Merkle trade will cost you a lot of money in transaction fee. And this is also not very nice because that the entire transaction will have a bunch of the copy paste of the opcode of the script that is doing the hash function. You basically repeat the same opcode, the same script multiple times in order to do that. And while that is still okay, you still can do that. It's just very inefficient. Covenant is not possible. The best way to say it is not that, okay, so many years later, people cannot find that. But it's actually easy to show why this is not possible because it's very easy to say that you cannot have a way to look at the rest of the transactions through other than going through signature verification because that's the only opcode that will allow you to touch with the rest of the transaction. But signature without opcat, what you can do with the signature is a black box. Basically, this is that you can check whether that signature is correct. You can check, let's say I give you 5 signatures. You can figure out which one of them actually work. But you cannot do something meaningful about the signature. Signature is almost like a random string. It doesn't have specific meaning, and that seems to be the only thing you can deal with the signature. But now I want to show you that with opcat, actually a lot of things become possible. So, Andrew is here, but basically is that an idea that was proposed a few years ago is that signature verification opcode, if you have opcat, you can actually turn it into a way to get some sort of a hash value of your the transaction that you are currently on. And the idea is this, is that well, let me perhaps say the idea, but roughly is that there is a way so that the signature that is being constructed is very similar to the hash function, hash value of a bunch of the variable inside inside that transaction. I think I will skip this slide. I will just go to the next slide. Basically, that using that trick, you'll be able to get what we call a SIG hash of the transaction. SIG hash is a hash of a bunch of the variable in the transaction. You have the airport, well, that is a dummy value, but you have version, log time. You also have information about input and outputs. And with this information, you can actually let the script to kind of start to know what is about this transaction. You provide information about this transaction as witness element into the script. The script will assemble them together, recompute the SIG hash, and compare this sig hash with the sig hash that you obtain from like the snort trick. And here is one thing is that so there is a critical step in the snort tree where you kind of need to put the public key here, and then you need to put one value there, and then you also need to modify the last byte. That poses a problem is that you kind of have to do that through opcode. So this is one of the reasons why snort tree type inherently require opcode. And another thing that requires opcode is to construct like this, like I would say pre-image of the sig hash so that you can do something meaningful about that. But with this, with like opcode, with this, you can actually allow the script to kind of like look at the input and look at the output. And this gives you an ability to, I would say, constrain input and output. Like when we talk about like covenant, usually we are only talking about constraining the output. That's requiring how the code can be spent. And this will allow you to have the ability to also restrict what will be the input of that transaction. And this, I use this diagram to show that. But basically, that one of the input, which is a script that is being executed, it can now place requirement on the output and also its neighbor. It can also place requirement on itself, like for example, where am I come from, right? So this start to give you one power is that like with sig hash, with opcode, you can start to look at the entire transaction that you are currently on. Well, it doesn't stop from there because that like if you can look at like yourself, you can also look at your transaction ID, what we call previous output. So because sig hash can give you information about the input, it also include information, very critical information about the input is where do they come from, and that would be your transaction ID. Transaction ID in Bitcoin is very useful because it's actually containing a bunch of, transaction ID is a hash value of like a succinct version of the transaction. It have version, it have like input, it also have output. It doesn't contain any weakness, so you cannot easily find the script from it, but you have the public key and everything you need. And like transaction ID, and this actually gives you yet another ability. If you can look at where you come from, you know the transaction ID, you can start to see what is in that previous transaction. And this will give you the ability that you don't just look at the input and output of the current transaction, you can also look at the parent of the inputs. And this kind of give you this ability is that now you can, let's say that like here, basically these two are actually the same same thing. This is the previous like output that generate this. It can now also look at like the parent, the previous transaction. By the way, it can also look at the other like inputs like parent. So you can actually look at like all the parent that is kind of connected to. And this will give you some sort of like covenant, like people usually call this recursive, but basically what can happen right now is that you can look at not just yourself, but your parent. And that also means that if you continue doing that, you can look all the way back to the Genesis like block if you want. Actually, no, let me tell you back. It doesn't guarantee that. I think there's no guarantee that it will happen. Okay, but back to this is that like okay, you can come back to a block where it was actually the code base like just being minted. Okay, and with this you can actually continue doing this. You have like a transaction. You can come to the parent come to the parent to the parent, and this kind of give you a chain of the transaction that is able to kind of carry the state. Okay. And with this, what are the things that you can do? Remember I talked about kind of 5 things that EVM have and Bitcoin doesn't have. Now I want to tell you why covenant can be used to do all of them. So first of all, you have state. The question is this, is that now that you have this structure, it's kind of useful that you can have like carry things around. Can you actually carry data with it? So that like the script is executing, it always know like what is the like transaction, what are the information before. Well, there is a way we call it like state taboo, but I think many different teams probably like have their own names for that. The idea is this, is that like if I need to carry data over, I probably just need to put the data somewhere in the parent. It's a little bit like, okay, I go back to my parents' house. In my room, in the parents' house, there's some information. And here is basically what happened, is that like, so as I mentioned before, this is the input, and this one is like when it was like the previous like output. Now, what they do is that in the neighbor of the previous transaction, I'm going to use this transaction to store additional information that I want to pass around. Basically, it's my previous state at that time. And I can use OP return to do that. There are also other ways not to use OP return because OP return is very easy to get filtered out right now. But basically that you can use like the neighbor to store the data. And then after your script is executed, you have the new state. All you need to do is to put that there. Basically that when you finish your computation, you become the new parent. And all you do is that you put the state also like somewhere in the output, and that like it will be an OP return. You will be OP return together with a hash of the state. And you can do that many, many times. And this will give you, for example, something like ERC20. By the way, firstly, this is not the best way to do ERC20. So if you heard about TABConf protocol, they actually prefer to use a more UTXO-based solution to do the ERC20 token, because the ERC20 is not really scalable. They find that actually use UTXO will be better. But come back to this, is that you can already build some sort of ERC20 with that. It's basically that, okay, you build a big Merkle tree. If a user wants to send or receive some token, you just update the Merkle tree. And that token transfer is just basically rewrite about the state that you are carrying. And you can update the state every time you are doing. Okay, that's the basic idea. There is a small problem about the state, how does user actually use that? But we will talk about that very quickly. Okay, the next thing is function calls. That is, how do you, in a transaction, involve probably two, I would say, Bitcoin smart contract or this covenant together. A very common example in a lot of the app, the app is probably that, okay, you want to have interaction with a stable coin or that another crypto currency, another token. Well, what you can do is something like this, is that, let's say I have a contract. This contract have functionality is that I probably will give you some ERC20 token, or here it's actually on Bitcoin. But the idea is that you can actually construct a transaction that is a little bit like this. You involved two of the recursive covenant in the same transaction. The first one is doing the logic, and the other one is actually let's say, the stable coins ERC20 recursive covenant. And what is happening here is that the contract will basically say that, okay, I do my job, I update the state, but I also are going to issue a request to the ERC20 recursive covenant, telling it that I'm going to send this user some token. What you do is this, is that, remember, because you have covenant, you can look at the input and look at the output. So what you can do is that, I will just repeat, give you a workflow, but basically that the first contract, you will look at the parent, get the previous state, compute the new state, and that make sure that the chain is forming correctly. And then you will use one of the output as the, this output is basically just the places where you pass the data. Basically that I will use this output to store some data, and that will be my communication channel with the other recursive covenant, which is the one below. Okay, and the contract is what? Now it's also you need to check that the real ERC20 is there. There is some way to do that. I will talk about that. Okay, actually it's right here. There is a way for the contract to recognize whether the other recursive covenant is the real covenant for that stable coin. I cannot provide all the detail, but TAB20 uses a similar way. Basically that you give each of the contract a unique ID. Okay. And now the stablecoin contract, it will be the one that actually updates the state. What it do is that, okay, it just do what the recursive covenant do. It look at the parent, it update the state, but also here, it look at the places where it would be the inter-contract communication channel, which is actually in the same transaction is the output. And you will also track that the contract is right there, is the one that actually write information into that channel. And if that is the case, you will update the state saying that, okay, the contract approved me to send some money to another one. This actually already give you one thing, is that now contract can own money, can own token as well. Okay, and finally, double check that the recursive covenant can continue. And if we want to do more about functional call, what we want is probably that we want to decide how is the actual way for this different recursive covenant to work. And I think this will require some work. But I want to say that TAB20 protocol can already have this functionality. I didn't do that, it's from a different team. as script, they implemented like the Cat20 protocol, and that one actually already have this like capability where like another one can have call and work with that smart contract. Okay, now is the big topic, concurrency. Because when I was using this diagram, I think people can immediately see a problem is that if multiple different users want to use this system at the same time, they will need to talk to each other. Otherwise, the UTSO that they are spending will be the same one, and only one of them will be able to go through. Well, there is a solution of that, is that like you can actually let the user construct the transaction in a different way, and that like we can actually have the miner help them. But firstly, let me just summarize what is the problem. Let's say that we have one recursive covenant that is doing like the stablecoin thing. Alice and Bob both want to call them. They actually see the same previous like transaction, basically the UTSO for that. They are going to send a transaction both using that UTSO. So only one of them will be successful. Well, the problem is that this would not work unless Alice and Bob talk to each other and they internally say that, okay, we will work with each other so that we have two transactions. Bob know that like what is the new UTSO that Alice generates, so Bob can continue from that. That is the idea that this will work, but this is very complicated. User need to talk to each other, and this also provide a lot of the like attack vector. And that like user need to talk to each other, user need to really assemble this thing together, and if like two different users actually form their own chain, maybe only one of them will be successful. Well, one idea is this, is that maybe we can find a mechanism where miner can have what we call sequencing of this thing. The idea is that, let's say, three different users all want to talk to like the ERC20 like thing. We will firstly find a way so that like basically all the users just write what you want to do down. Don't call the ERC20. Just write down. And then the miner will be the one, miner or sequencer, or if later you have some sort of like bundler, they will be the one that do the rest of the work. Is that, okay, everyone, the submission, I already saw that in the mempool. Now I will aggregate all the things together, and I will just do the work for you. I will talk to the ERC20 and submit all your requests together. This solves the problem because the transaction that Alice, Bob, and Carol are sending are not really related to the like ERC20 that they are using. They use a script to make sure that like what they send can only be used for a specific purpose. But here, the key thing is that like the transaction Alice, Bob, and Carol are sending, they are independent. They don't depend on each other. They also don't consume some UTSO. Here, the white box that I'm using basically say that like it can be just anything with the money that pays the transaction fee. Yeah, and that will be aggregated by the miner. Miner will do the sequencing. By the way, miner is always doing the sequencing, but here, miner will be the one that do a little bit more work in that the miner is actually creating transaction. Okay. And that like why we still need this is because that why we still need this transaction just for Bob to say what he want to do. This is more for the purpose of collecting a like signature from Bob so that we know that Bob actually want to do that. Like the submission UTSO, when it was being like used in a later step, it will actually also do what the recursive covenant do. You will loop back to the previous transaction, making sure that Bob as the owner actually signed that transaction so that Bob actually want to do that. Okay. If you have function call, this will still work. It just start to be a little bit more complicated. So here in this graph, while like blue is one recursive covenant, like orange one and yellow one is another one. And let's say that the miner already decided that this will be the sequence of the like transaction that I want to like follow. Well, it will do the following. First of all, the first four are the same, right? It can merge them, and that like this will update the like blue like recursive covenant. Then you have like the orange one. You can basically also update, you get the orange one, and then you send the blue one. This will be the next one. You have another blue one. And for the green one, you will do that independently, but the like blue one can, so here the blue one can also come from the previous one, and the yellow and the orange one like this. But basically that like when you have function call that involve different transactions together, it's a little bit tricky, but the miner still will be able to find a way to have sequence that. Okay. So, and here is one thing that is important to mention is that in Bitcoin, you can actually have transaction that basically that like the output of a transaction in the block can be also the input of a transaction in the same block, as long as that the other one is behind it. So miner can actually do all of this in the same block. Okay, with concurrency, well, clearly, as I say, that if you want a miner to do that, like this will be a little bit attack better, like NEV attack. Here, I firstly want to mention that miner can already do that today. Miner are doing the sequencing, right? Like transactions sent to the mempool, they will be the one to decide the order. Like the concurrency here is that like maybe there are ways so that like we also don't need to worry too much about the fact that miner can now decide the sequence of all these transactions. First of all, like it's kind of a semi-solution to NEV is that you let everyone to be able to do NEV. Is that like, first of all, they are miner, right? Miner are random, so the next miner might be good enough so that they will take the transaction honestly. That's one way. At least the NEV benefit is being evenly distributed among the mining power. Another way, you appoint a designated bundler or a bunch of the bundler. They probably are doing like proof of stake or something. They become a bundler and they will be the one doing bundling. The first one, decentralizing the AV, doesn't solve the MEV problem. It just makes sure that everyone gets a share of that so everyone is happy. The second solution is to discourage like NEV by proof of work. This is very complicated. I don't have the full like, idea, but the idea would be like this is that you assemble all the transactions that should be processed like somewhere, and you type sort them according to the transaction ID. So you basically just have a like sorted order of them. And in the next block, you use the block header to sort them again, basically shuffle them. And the next block will be required to process this transaction following exactly the order that the block header have like an influence over that. Still, miner might be able to influence that. Miner might say that, okay, let me mine another block so that my transaction will get to another position. But miner will need to spend some effort in order to do that. So the second solution is basically that you use the block header as a way to kind of randomize the order of the transaction. It is not perfect. Miner may just try very hard to kind of change the order again, but this will be a way that at least make the NEV attack not as easy as like it didn't just be the miner. Okay, I will now talk about like crypto accelerator, but I am actually mostly talking about Merkle tree. Bitcoin do have like the hash opcode. The problem is that it's not really useful because there are only two things it can do without opcode. It can hash anything that is not a hash into a hash. It can also hash a hash multiple times. This is kind of already kind of useful already because if you can hash a hash multiple times, this gives you witness like signature. But this doesn't give you Merkle tree. Well, if you have OP tag, immediately all the problems are solved because if you have OP tag, you can let you can make the hash opcode much more powerful in that they can, first of all, they can even hash a non-hash like element and a hash element together into a hash. They can hash two hash together into a hash, which will be the use case that like is very common in Merkle tree. So with opcodes, like a lot of the I would say is just making all the crypto like opcode much more useful than before. Okay. The lastly, send receive money. This is probably the easy example is that with Covenant, the script can see where, like, did someone send the money in the second input, so it can take money. And you can also make sure that, okay, the money eventually go to myself by looking at the balance of the output. Okay, and you can also send money. This will be even easier is that, okay, it just makes sure that, like, oh, I look at the output, yeah, I want to send that, and you approve that. So this will be the easier one. With Covenant, you just need to look at the input and the output. Okay, now I will start to talk about like some stuff about like how OPCAD, if you want to test that, how to use that today. There are about 4 networks that have OPCAD right now. You have Liquid. Liquid is a little bit different from Bitcoin that it has many more opcode, and that like the protocol is slightly different. It's not because you can arguably say that Liquid actually was running by Bitcoin because like the native token there is one pair with the Bitcoin. You have Bitcoin SV, it's a different token. The TVL actually looks okay actually. It's different from Bitcoin also that like it have much larger block size and also the opcode is very, very different. You have Fractal Mana, which is the one I think just go live within the past 2 months. It's still a much smaller network. They are also not using Bitcoin as the native currency. But a good thing about that is that it's very similar to Bitcoin because it deviates from Bitcoin only by adding the like opcode. Lastly, you have the Bitcoin signet. This one is a testnet. is that the token is not real money. But it would also deviate from the Bitcoin, but it have 3 more things. It have like check complete verify. It have opcode. It also have like any previous output. So it will be the places where you can start to test your implementation. Actually, a lot of the enthusiasm right now is on Flatto mainnet because they do a lot of the user I will not say farming activity, user engagement activity, so that there are actually a lot of the user playing with Flatto right now. Okay, and people were wondering how expensive the covenant is. That how practical? We actually do a simple example to show that this is a recursive covenant that do a very boring thing. It maintains a counter, and what it do is that you can let the recursive covenant update the counter. You can let it update by 1. You can increase the counter by 1. You can increase by 2. You can also increase it by a number that you provide that is smaller than 100. And what we do, this will be the real transaction that I think we already execute that on signet. You can change that from 1 to 2 to 4, and you can now adding 99 to it, add another 1. And that if you are doing this, basically this is I think it's the simplest example of doing recursive covenant. You just change very small number, but you actually, by doing that, you look at yourself and look at your parent. You basically cost 0.55 dollar in terms of transaction fee, assuming a fee rate of 2 cents per byte. And that I consider this to be fairly cheap compared with the application that you might actually want to do over that. Okay, and BVM will benefit from opcode. The main reason is that BVM have that trusted setup. With opcode, you don't need to do that anymore. You also don't need to use lamport signature, Winterny signature, because you can use the state construction that is right here. And for example, in BVM, you need to do the challenge, that will be deposit. That will have to do with the lamport signature, Winterny signature overhead. Now with opcode, all this will start to go down. And BVM still is useful because I think BVM have represent a way that is useful to secure the system. And with opcode, it will just be much cheaper. And opcode have substitute check can be verified. By that, it basically means that if you don't have check can be verified, but you want to use it, you can use opcode to simulate it. Opcode basically pull all the information about the input, and that it start to put them together to assemble the output of that. By the way, there are always limitations. Opcode will have restriction on where the transaction cannot be too long. Otherwise, it may not work very well. But in most of the cases, this should be work. If you want CTV, opcode will actually allow you to do that. CTV is known to be weaker than opcode because CTV was designed so that it doesn't enable recursive covenant, but only covenant, where opcode enable both both. Okay, and if you want to think about any previous output, I need to say that opcode doesn't really replace that. Why? So any previous output is one of the SIG hash options that have been discussing for, I think, probably a few years. The idea is that allowing us to create a signature that doesn't cite the previous output's transaction ID and the other information. This will allow a signature to be useful for multiple transactions. The opcode can only slightly help with that because if you have any previous output, it gives the user an ability to cite a specific type of the signature. But opcode cannot actually really help with that because even if you have opcode, the check signet verify function still are being forced to take the previous output as a required information in the SIG hash. So if you want to you really want the full version of the any previous output, you need to emulate small signature verification inside the contract, which will be quite expensive. So I would say that if you are thinking about building application over any previous output, it will not be easy. With opcode, you will be designing the protocol using a different way, and it usually should work, rather than really following exactly what any previous output want to do. Okay, the last part of our call is talking about layer 2 and the work that we do about Bitcoin ZK verifier. There are reasons that we want to do layer 2. I think probably the key reason is scalability, because I think it's very easy to argue that Bitcoin have limited size. Even if you make the script language extremely powerful, you still cannot process that much transaction like every block. So this will be a strong reason is that even if Bitcoin become more powerful, if this is still like the block size, maybe you want to consider a layer 2. And this is also consistent with what we do with Lightning Network. The idea is that you shouldn't use Bitcoin to do some very boring stuff. If you can do off-chain communication, you should be allowed to do that. That is kind of the similar idea. Layer 2 can also provide things that are beyond scalability. Like for example, latency. This is one of the big reasons why a lot of users are using Flatop mainnet, because the latency is much less shorter. You also have more functionality related to sequencing, account abstraction. You can also have smart contract. Like that will also make it easy for developer. You can also not be restricted into using Bitcoin script. You probably can say that I'm building a layer 2 with EVM, with water, or maybe you can choose a lot of the language to work on, and this will be easier for the developer. BBM will be an option to do layer. Well, it will be an option to do layer 2, but it's not as like ideal. These are 3 reasons, and these like 3 limitations of the BBM like bridges, and this was actually from the BBM bridge paper. The first thing is that like you make sure you need, like in BBM, you always need to make sure that at least one of the operator is live. Otherwise, the protocol really will die. Like no one can like recover it back. And the second thing is that like the amount of the money that the user pay in will need to be decided during the setup. The last one is that operator does need to have some liquidity in order to kind of give the money to the user and wait 2 weeks later to get the money back from like the BBM like finalization. And this is basically some of the problem that BBM bridge will have. I think probably the main issue is about the unilateral asset, is that if you want the user not to trust anybody and will be able to get the money out, BBM is not have designed to enable that. But like other than these 3, most of the like issue that people might be thinking that, oh, BBM might be not practical for Ether, that I think today, we think most of the other problems all have solution right now. So these are basically the only problem of the BBM like bridges at this moment. And talking about that is that like, if you use layer 2, if you don't want to use like the BBM-based solution, you can also think about things like ZK. There are 2 types of the ZK algorithm. One we call stack, or basically is that like it's basically zero-knowledge proof based on hash function. And another one is not based on hash function, but based on like elliptic curves. These are basically 2 ways for you to do ZK right now. I can basically give you a number is that like if you have opcode, very important, you need to have opcode. Hash-based ZK can be done very efficiently. Probably you only need several megabytes of the script. Well, clearly that's larger than a block, so we'll talk about something to make it cheaper. But if you do elliptic curve, the script size is something probably like 2 gigabytes. So you are not going to really execute that on the blockchain directly. But remember one thing is that like if you borrow a little bit like trust model from like BBM, assuming that there is going to be a global watchtower that watch only one smart contract, then you can also do like basically what we call optimistic ZK proof verification. Basically that you post the proof and you make it like verifiable or challengeable. And if someone saw the proof and think that it's not right, you can challenge that. This will actually be able to do, basically you still have the benefit of ZK. Like for example, you can build any type of the layer 2 that you want. And with the benefit that now the cost will be basically disappearing. As long as the proof is valid itself, there is no cost, basically no cost at all for you to do this. So like, I think here I can do a very quick summary is that if you are doing like hash-based ZK, this will be possible, but it will cost some money to do that. And you will probably need a few transactions in order to settle down on the like, blockchain. It will cost some space on the layer 1. If you are using elliptic curve base, I think you will have to do this like optimistic ZK proof verification that I mentioned. And like we did a little bit work in like how to kind of implement a verifier for ZK over like Bitcoin with opcode. Like, so we kind of designed, I would not say designed it because that like all the proof systems are similar. So they are kind of not really new things. We kind of designed it like a proof system called Circle Plonk. Is to replace a few things from like the popular Plonk like proof system by firstly using stack, use hash function because it's more efficient. And like we also made the circuit a little bit simpler in order to reduce like the cost over Bitcoin. And it supports something called R1CS, but basically this R1CS is basically the one that is behind the programming language for like Zcash. So basically Zcash was done using R1CS, and that like if you are familiar with like ZK programming, then that most of the like programming language that people use to write ZK circuit, you can easily compile that into this like new like verifier. And if you want to verify, we have an example that already done on signet and flatto like mainnet, is that if you have a small like circle prompt proof, verifying that would take about 3.6 megabyte of the like script. And if we assume that we are doing that on Bitcoin mainnet, that would be about $1,000 to do that. If you reuse the Bitcoin proof of work, I didn't talk about that like today, but basically that's a way to reuse Bitcoin to do a little bit proof of work. By basically changing the proof protocol into a more interactive one, you'll be able to reduce the cost to about 600 to verify ZK proof. If you want to do optimistic ZK rollup, assuming that there's a global watchtower, by the way, this watchtower doesn't need to know anyone's secret. It just look at the proof. This one can be very cheap. It will go down very significantly to probably just $1 to $2. Okay. And I think lastly, I just want to share how do we have create this verifier and why you can also do that. So, when we start to write the Bitcoin like verifier, we actually write that by, I will not say by hand, you already have some cooling, but it's kind of really like you are facing the opcode every day and you are calculating the distance between like the stack element. But we eventually started that we want to use like an embedded DSL. Embedded DSL is a very fancy word. There's another way to call it. It's called library. But basically that we so the current version of the verifier, this is the real code, is that you can use a very Rust, basically an interface that is very similar to Rust to write all of that. When you want to add number together, actually these are not Bitcoin numbers. These are actually few elements. They are like few extensions in the ZK. You just need to write at minus, and the DSL, which actually is Rust itself, will be able to generate the Bitcoin script that did that. And you can also do hashing. We made it very friendly. If you want to hash something, you just add them together. And we also build some sort of memory. Basically, that if you have opcode, remember I mentioned that opcode will give you the state, right? You can make that state a key value storage. And you can have a very easy way so that if you want to pass data to many different transactions, here what I do is that I can read something from the previous storage. I do time computation over that, and I write it back. And that's what the memory here is doing. This is a DSL that fully rely on opcode, but it will give you a lot of things really useful here. First of all, if you have complicated operation, you can have write the Rust abstraction so that you can just add minus on them. And if you want to do hashing, you can also make it look very nicely. If you want to do memory, you can also have a way so that it give you back key value memory. Oh, 1 minute, okay. We also recently attempt to write Blake with that. It's very difficult though. Blake is complicated. But basically that you can when we write the G function, which is a bunch of the XOR and something, you can also write it in a simple way. The table is the lookup table, which I will not be talking about the detail, but this is a table-based implementation. And if you want to rotate right shift in Blake 3, this one also gives you an easy way to write the code. Basically, just rearrange the element in the stack. This actually doesn't change anything on the stack. They just have changed the index. Okay, and the next step that we will be doing is that we are looking into reusing Bitcoin proof of work. That will reduce the cost. We're also trying to improve the transaction flow so that miner will not really filter out the transaction as much. And that we also are thinking about that foolproof version or optimistic ZK verifier version so that if you have opcode, assuming a watchtower, the cost will go to very low. And that there are also other things that we are doing. The last thing that we are also thinking about the Starkware is also worrying a lot about opcode doesn't work. So they are also asking whether you can do stack in BPM if opcode is not happening. So, and so this will be the conclusion, the end of my talk. We have the GitHub repo. Everything we do is open source. I'm the MIT license. And that we also have a Telegram group that we'll just share a lot of the news. There are about 100 people there, and if you are interested, you can also join that. Okay, I think it's a good time to take like, I have time for question or no?
Yeah, we can take one question. Anybody's got a question? All right, big round of applause.
Okay.